Okay, guys, can you hear me? Hi, thank you very much for joining. I lived in New York for 14 years, moved to Bangkok 3 years ago for Agoda. Belongs to Booking Holdings, one of the biggest, actually the biggest travel website in the world. The entire Booking Holdings, so there's 10 different brands under the hood. So Booking, Priceline, Agoda, rental cars, OpenTable, and so many more. I'm used to the on-conference from New York City. I've been coding in Scala since 2009, so I started with 2.8. I'm a senior manager at Agoda. I converted quite a few teams already to Scala in the last 10 years. Anything from PHP developers, Perl developers, Java developers, C# developers, C++ developers. Interestingly, the Java developers are the most difficult ones to convert. Everything is so Java that they end up writing Java code in Scala. So what I wanted to say is that I'm used to the New York City on-conference structure, which is very, very casual. So there's a lot of feedback. There's a lot of questions. So I'm going to tailor everything I present. I have a lot of stuff to present, so basically you guys pick and choose what you want to see. I remember my first on-conference, I ended up I had a startup in New York City. I ended up doing the architecture and the design with the CTO of Twitter, and then chat with the CTO of Foursquare. So it's a very dialogue-based meeting. So I was looking forward to coming to Tokyo for this as well, and happy to see that we have one here as well. Okay, so I'm in the industry for just a little bit of a presentation about myself, and then I'll dig into. So I have the real-time monitoring deck here, what I do for Agoda. I also have the anomaly detection deck as well, so we can drill into the anomaly detection later on, but like after this. So I'm the guy who they call when they have a lot of data and then a lot of problems with it. So actually, I used to work for Samsung Research before joining Agoda. And before that, Bellcore, Bell Labs, Morgan Stanley, everybody has problems with data, a lot of data. So actually, at Agoda, they reached out to me and said, hey, we have this real-time monitoring system, this platform. We in-housed it, so we built it from scratch. It's Scala, mostly, ugly Scala, and a bit of Cassandra, a bit of Kafka, and it's falling apart. We need to take it to 5 million and above. And that's what I ended up doing. So I'll present you the architecture. I'll show a bit of Scala here and there, but I think the key takeaways are what to use, what not to use. And my business cards are there, so if you just grab one on your way out. And if you have any questions later on, or if you need anything I can help with, I'll be more than happy to. All right, so for Agoda, I run 3 teams and 5 products. So I'll be presenting one. Real-time monitoring. Okay, so Agoda is 4,000 something people company, out of which 1,200 are developers, running about 400 something, close to 500 microservices. So we really, really embrace the notion of microservices. We run our own private clouds. So we have 5 data centers, all run by us. We own everything, hardware, everything. Everything is HP. Most of the machines are CentOS, and then the rest is Windows. That's 20,000 servers, VMs, bare metal, and whatnot. And yeah, that's it. So basically, I'm the guy who's collecting all the performance metrics that exist in Agoda, and that means about 8-9 million metrics per second. So why did we? If you look at the background, you'll see different names. So those are other real-time time series engines that are out there. When we built this 5 years ago, there was basically only Splunk and InfluxDB, not really, more like Graphite actually, and it was just none of them really worked for us. Either too expensive or just really not supporting the scale. So one of the key things why we ended up building this ourselves is that we have this multi-DC tendency. So we try to keep all the data localized in the DC that's relevant because we're a global website. So basically, if you're in the US, then you'll be served by the Ashburn servers, which are next to Washington, DC. If you're in this area, then it's probably Hong Kong or a bit of Shanghai or Singapore. If you're in Europe, it's Amsterdam. Why Amsterdam? Because we belong to Booking. Booking is in Amsterdam. So we share, actually, a lot of our servers are co-located. Yeah, so this was very important for us to just be able to have this multi-DC support. You'll see in a slide later on, any of the API nodes that I own, you can hit them and query for any data, and you'll get it from anywhere in the world. So it's very transparent for everybody. Horizontal scalability, auto-rebalance, these are very, very important for us. My weak point is actually Cassandra, and I guess a bit Kafka, but so everything else would automatically scale and rebalance. When it comes to real-time metrics, and if you're in the business of it, I very strongly recommend you look into this. There are different types of aggregate data structures. So like for instance, yeah, you obviously have the sum count, so the more raw numbers, but you also have percentile. So percentile is actually very important. So I have a couple of slides later on why. Another data type is distinct count, cardinality, right? And for instance, Google's Hyperlog logger implements this. So we ended up implementing all these in our system. Another thing that we appreciated about in-housing is obviously picking the tech stack ourselves. So everything is Scala, everything is Cassandra, Kafka, and people love this or they want to pick this up. So it's fairly easy to hire new people or have other people work on this. All right, so what exactly is real-time monitoring? Eventually, you have a client library that's either Scala, like we have our own Scala library, .NET library, Go library, and then all you have to do is basically say, okay, this is my metric, these are my tags. Think of tags as a hash map, basically, like all your dimensions for that specific metric, and I want to send it. That's it. I just call send. I don't care where it goes. I don't care what happens behind the scenes, but I want to see my data as quick as possible. So my current SLA is 2.5 minutes. I need to, in this quarter, I need to take that down under a minute. And obviously, you get to see your metrics. I can do a quick demo just to understand. So the thing that was very, very important for me, so the team is, this specific team is 6 people. I needed to make sure that this is as self-serve as possible. So this is an advice for you guys. Everything is self-serve. So the library is there. All you have to do is just use it. I don't get called, hey, how do I use this? What happens? And same when you consume the data. So you just go to Grafana. This is actually production. I'm VPN into the network. When somebody's interested in something, all they have to do is create a dashboard, graph. Right, my data source default. Let's pull front end page load time. Not sure if I'm allowed to share this with you guys. So that's load time. Let's say I want to group by server. So I'm pulling last 6 hours worth of load times for all the servers that are serving a Go-To website. Let's say I'm going to filter only on Hong Kong, DC. So what you see here is like all these things where you have autocomplete and then you have all, like we forked Grafana and then we basically added a lot of goodies to Grafana in order to integrate very nicely with this real-time time series that we built. All right, now I'm just gonna, that's pretty much it. So I could, obviously I'm gonna change the name because right now it's horrible. I want to actually see the servers. So these are all the servers. As you can see, we have quite a few, right? And then set my time This is, I believe, microseconds, and there you go. So this is what's happening, right? And actually, if you check right now, we're somewhere there. So it's this easy, right? So I don't need to do anything. People just come, they create their own dashboards. We ended up with 5,000 dashboards. And then some of them were being refreshed every 10 seconds, every minute, so pretty much everything. Okay, so back to the presentation. So what am I storing, right? So I'm storing all the performance measurements. That's operating system level, VM level, CPU, memory, you name it, context switches. One level above, JVM level, where I'm running JVMs. One level above, service level, throughput, lag, you name it, cache hit ratios, whatnot. And even above that, also business data. So what we managed to build here is something that's good for both IT and non-IT. The entire company is using this. And again, my SLA is 3 minutes. Everything is self-serve. So if you do build something for a company, especially at this size, make sure it's self-serve so that you don't get a lot of calls and a lot of, how does this work? What do I do? So the actual landscape is, we're having many time series. So not just that eagle there is a White Falcon, it's my product, the time series product. But we're also pulling time series from Postgres, from Prometheus, MS SQL, Elasticsearch, Graphite. So we all have these in the company. Everything ends up visualized in Grafana. There are a couple of programmatic clients as well that pull data. And then we actually built our own alerting system on top of Grafana. So Grafana 5 has it, and it's pretty good. But we built this 3-4 years ago. And obviously all the clients that connect to it, we push all the alerts through to OpsGenie as well. So just in case our systems are all down, you still have the alerts available in OpsGenie, an outside system basically. All right, so what is a measurement? What people send in? So a measurement is log time, when did it happen, where does it come from, what server, what is the actual metric, what is the actual value, right? And then the tag, hash map that I mentioned. So all they have to do is this, those 4 lines, and done, nothing else. What this actually looks like, we moved away from JSON to Avro, and it's a huge improvement. So I very highly recommend you guys do so if you didn't just yet. But yeah, this is the JSON representation of what I get. So I see about 8-9 million of these per second. And then everything gets aggregated up. I'll show you in 2 slides the actual data flow and then the architecture. The idea is that I aggregate everything up to 1 minute buckets. So like 700, the 3 measurements for 700 get aggregated into 1 aggregate. And then the 701 lives on its own. So all these measurements end up in these aggregate measurements. It's like minutely buckets of sum and count. But as I mentioned, we have these server-side aggregate types. So not just sum and count, but percentile and cardinality as well. I'll explain you why I have 2 sum and counts in a bit. So I end up with all these different combinations. 1 minute aggregates, 5 minute, 10 minute, 1 hour, 12 hour, with different retention periods depending on the business needs. Right? So it could be 1 quarter, 1 year, 1 month. I also have projections, so that's the second sum and count. So think of projections as materialized views. So if I notice, based on how they query, so I collect query statistics. I understand how people query this, then I auto-create projections. So if out of 10 tags, you're interested only in 2 tags, you constantly query 2 tags, then I'll also automatically build behind the scenes a materialized view on those 2 tags. So a couple of statistics. Total storage on this side, 1.1 petabyte. Some of it ends up in Hadoop as well. So our Hadoop clusters are, I think, 15 petabytes right now. I'm at 26% storage, so there's plenty of room left. So different distinct metrics, about 10,000 that people send in. Different tag keys. Think of a tag key as a dimension. about 60,000. Total distinct tag values, 6 million. So on average, about 6 dimensions per metric. All right, so this is, let's get to the meat of it. This is how the ingestion bit happens. So I'll explain later how we query, but this is how we put the data in. So you see the clients. So I said 20,000 VMs and bare metal servers, each running 1 or 2 or multiple services, are sending all this data into Kafka. So we have our own clients that basically pick this thing up and then forward it into Kafka in each DC. Then I have the aggregators, everything Scala. So I'll dig into that in a bit. So we aggregate up to 1-minute buckets, the slide that I showed you. Then we push it back into Kafka, and I'll explain you why. And then pull it from Kafka again, and then have writers that actually write all this data into Cassandra. And then in parallel, I also have these meta writers and meta analyzers to actually understand the nature of the data, which helps the query optimizer to know can I run this query? So basically I have a cap right now at about 600,000 data points per query. So what I showed you there, the 6 hours, that was running over a couple of hundred servers. Like if you start to add up, you'll see that things add up pretty quickly. So the two-stage thing is quite important, and I'll get to it in a second. But the idea is that you have a lot of data coming in through Kafka, and I'll show you a slide where we partitioned each topic. It has about 64 different partitions, and the hashing is basically done by metric and then the tags, which provides a fairly a fair share, a fair distribution. But the problem is that after you aggregate, right, your distribution is completely different. Like some things aggregate very nicely, some things don't aggregate at all. So what the aggregators are pushing at that point may be very skewed, and it is quite skewed actually. So that's why we write back to Kafka. And then due to that, Kafka basically everything gets rebalanced again. And then the writers get a healthy, balanced aggregate data at that point that ends up in Cassandra. All right, some statistics. So my KPI is be under 3 minutes. Again, this is changing. And then these are the rough numbers. So what matters most to you is the last line. So this is Scala. So that translates to about 250,000 measurements collected, aggregated, and synced per an 8-core machine. So that's pure Scala. And that's where some of the magic happens. When it comes to, so this is another very important thing that we did. The notion of data availability, that's available right away. So yeah, we get this data, but we also write everything at the same time. So I'm already creating the projection. I'm already writing into projections as well as I write to my raw data. And I already write the cardinality as well. So this is the real-time bit. So for the cost-based optimizer, I can pick this up within a minute and then use it as dashboards are querying for, okay, what happened in the last 5 minutes, 10 minutes. Okay, so I mentioned this two-stage thing. So you see, so these are the two Kafkas, right? It's actually the same cluster, but different topics. These are the aggregators and then the writers that write to Cassandra. Basically, we cared a lot for scalability. So the horizontal scalability means I can spin up as many aggregators as I want. Same with the writers. Obviously, you're bound by partition, the number of partitions. But this automatically rebalances itself. So if I have, as I mentioned, 64 partitions and I have 8 aggregators, I'll end up with 1 aggregator pulling from 8 partitions. If one aggregator gets hosed, dies, we run our own servers, and they do die very often. So I just got an email and an alert, hey, this server just died. Okay, fine. So instead of 8, now I'm running 7 aggregators. It rebalances itself nicely, continues. The idea is that we're moving towards Kubernetes now. So I'll have a nominal basic amount of aggregators and writers, which I know guarantee my capacity. But I'll also have the capability of bringing up extra pods as more data comes at me. as in case of a spike or something like that. So again, I mentioned the fair distribution. So the metrics and tags as they come in, it's so much data that it is fairly distributed, roughly. Aggregation, as I mentioned, can change what gets pushed again, and that's where redistribution fairness happens again, and then basically what the writers get, that gets pushed into Cassandra are again rebalanced. So I don't care how many aggregators or writers die, or it just works. Okay, so damage control. This is where I'm moving towards RX streams. There are quite a few options out there for Scala. I just saw somebody with a type level t-shirt, which is awesome. I very highly recommend type level projects in general. I ended up embracing Monix, but there's also FS2, so please look into both. I'm not really sure why RX streams are not much more popular than they are, why there's no more buzz about it. When I took over the system, it was basically a mixture of Akka and futures. So there's a very long discussion what Akka is and what Akka isn't. So I have success stories with it and then really major failures as well. But what RX streams basically bring is the ability to build, they natively support back pressure, and that's really key, especially when I'll show you the next slide. It's really, really key because so this is the aggregators, right? So Kafka to Kafka aggregators. What happens is that if for whatever reason I cannot sync anymore, right? Or I cannot write to Cassandra, I shouldn't collect data anymore. Doesn't make sense, right? So the RX streams will automatically take care of this. So they will just slow everything down, right? And I'll get alerts of throughput, basically. Okay, my throughput is down. I cannot aggregate 250,000 measurements at that point. But nothing dies miserably. I'm not losing data. Everything is still there, right? Another thing that we built in, so the sync rates are basically defining the speed, but we also built in a memory pressure. Back pressure. So if for whatever reason, because I have to basically sync this every minute. So I collect as fast as I can, and then I sync every minute, the minutely buckets. But if for whatever reason my cardinality is really, really bad, and now I'm filling up the memory, then I have this mechanism of just dumping the data even sooner. I might be dumping it, pushing it over every 10 seconds if I have to. And obviously I have alerts for that as well. So the idea is that both FS2 and Monix, they're much more than just reactive streaming libraries. So they're basically asynchronicity, I hate this word, asynchronicity libraries, where you have all these building blocks, all these like task, cancelable, observable, observer, like all these building blocks with a lot of operators that could actually, they're literally building blocks. Like you're just putting together whatever you want. So we have a couple of helper classes and a couple of utilities around it, but in the end, all of it just ended up being, and I'll show you a bit of code as well, we just put together the pipeline nicely with all these operators. And you basically have to, like, you see the different phases, like the deserializer, the distributor, the aggregators. This is one of the cases where one of the aggregators, for instance, runs really hot on a CPU, and that specific line slows down. But that doesn't mean that everything else should slow down. So what is really cool about Monix, for instance, is that you can also pick the scheduler and then plug in your different thread pools at different phases as you build this. So it's really easy. Like once you embraced it and you understood it, it's very easy to build very healthy asynchronous multi-threaded things that just work. Okay, so this I'm not going to dig in too much. So afterwards, if you're interested, I'll be happy to explain more. But we have our own data model for for storing all this in Cassandra as well. So there are 3 different table types. Metadata is the cardinality bit. So this is what the query optimizer on this queries to understand what it needs to do. Index stores are basically indexes, and then the data stores are the actual data bearers, right? In this case, I put the total count, total sum, the blue stuff, which is the raw sum count. But there I would otherwise have a blob where I would store the t-digest, the percentile, or the hyperlog log, the cardinality bit. What you need to, I think the key takeaway from here is Cassandra is very powerful. As long as you truly embrace the whole clustering, primary, partitioning key, if you understand this and how to put it together, then it could bring a lot of value to it. Except for one thing, it is a JVM-based solution, so good luck with garbage collection, especially when you run many, many bytes of things. But for that use case, you have the C++ version, the Scala, which is I very highly recommend it. We did a couple of POCs internally in Agora, and it seems to work out pretty well for us. All right, so this is a concrete example of how data is being stored here. So again, I don't really want to spend much time on this, but I'll be happy to explain later if anybody has a question. Okay, so on the other side, so now we have all the data in Cassandra. Great. So how do we pull this out? This is the pipeline, basically, the different components for it. So the API is pulling the data, right? Goes through HEProxy, ends up in Grafana. And then I'm pushing into Kafka my query logs. If you don't recognize the Tiger, that's another time series engine. So that's TimescaleDB. So this is where I understand how people are actually using the data and what do I need to do to make it even quicker. So auto-creating projections, for instance. Some statistics on the API. So I have 2 KPIs there, uptime and coverage. I have to cover 3 nines. As I said, 5,200 dashboards, and then the rest of the statistics. Within the DC, my P99 response time is half a second. Cross DC, 3.5 seconds, especially Hong Kong, Washington, when the data goes like this. All right, so this is how a request looks like. It's exactly what we did 10 minutes ago. So give me my page load time, my granularity is minutely. I want to cover this period of time. And I'm looking for AGW, the Web 2E wildcard servers. And then the API basically returns this. As I mentioned, one of the reasons why we in-housed this was the capability of actually federating this, naturally federating all the data. So it doesn't matter which API you hit, you'll get any data from any DC. All right, so technology highlights. It's kind of it's the same thing. So I use the same library, Monix. Monix integrates very nicely. So maybe you've seen the Graal presentation from Flavio yesterday. So he wrote Quill. So Quill actually under the hood, well, depending on which Quill which flavor you're using, but the Cassandra Quill is actually using Monix under the hood. So I have Monix type elements being exposed to me if I want to. Observer, observable, task, and so on. So now that I mentioned about tasks, so for instance, we stopped using futures because one of the, two of the things with futures is that once you create the future, it's just going to execute. You kind of lose control of it. With a task, you set it up and then you attach it to some executor, something to do with it. So you don't really lose control over, okay, this is happening now. I cannot do anything about it. I cannot stop it. Also, a task is cancelable, which is not the case with futures. All right, so same back pressure built into the API as well. So the big challenge with the APIs is how do I pull 400,000 data points and then aggregate them up into 200 or 500 actual data points that end up on Grafana. And I have to pull this from multiple DCs and then so there's a lot of trickery that needs to be done so that you don't run out of memory, right? And then you serve it in a decent amount of time. Okay, so these are the steps that the query engine actually executes. So I validate the request, check, do I have any projections that match this specific query? So I'm trying not to go to the raw data as much as possible. Understand the I/O cost of the whole thing, assemble tasks. So these RX streams basically allow for a very nice, like you can fan out and then pull it back in, and then fan out and pull it back in, and then put async blocks in between, and then run different things on different thread pools very, very nicely. And in this case, it's really important for me because I have to understand what is my I/O cost for a certain query, but at the same time, I need to understand where's my data, which index stores do I need to hit, and I may need to hit 50,000 index stores. And again, there's a lot of reducing and a lot of picking IDs, and then going back to the data stores, pulling data, merging as I get the data as quick as possible so that I don't run out of memory. And basically, the code for this ends up being what you see there. Unfortunately, none of this is public, but I could show you little snippets of things. So this is the bit that I just showed you. So everything ends up being here. And then the actual specific query pipeline is here. So as you can see, there's basically operator of operator on operator. So map async, flat map, fold left, reduce. After looking at it for many months, it becomes easy to read. It's a bit busy now, but yeah. And then for the other thing, the ingestion, the aggregator. So this is the actual pipeline here. What I explained to you with the pulling, aggregating, having the back pressure embedded. So the actual amount of code is not that much. Also, I used Monix released Kafka Monix, which also exposes observables and tasks and whatnot. So I have Quill, I have Kafka Monix, and I have Monix itself. So I had to put all these three together, and then everything talks the same language. Okay, I have a couple of extra slides on tdigest. It's one of the most popular things with this. People really care for percentile. So basically, a tdigest is a data structure that holds percentile data. It's basically couples of mean, count, and you have two operations here: the add and query. Add is online. And then this is how it actually looks like when you add. So I'm adding to a tdigest a value of 2, and then a value of 4, and then an 8, and a 6, and a 12, and a 16. The actual algorithm is on the right side. So you see how it builds these centroids around the 50 percentile, which is kind of average-ish. It doesn't really care for precision as much as to the actual extremes, because what you care for is 99 percentile, 99.9 percentile. So what is my couple of worst services, servers, whatnot. And then when you query from tdigest, this is what it ends up doing. I have another slide, and I'm going to wrap this up. This is what costs for me to run all this. So in each DC, so as you see, like $500,000 in Hong Kong. This is my main DC per year, 250, 250, and so on. So roughly, this is about $1.4 million per year to run this, which does not include a team of 6, a salary for a team of 6. if you try to do anything else, like InfluxDB or whatever, you'll end up spending way, way, way more. Obviously, this is a lot of data spread all over the world, being queried by a lot of people. So I think that's it for the real-time monitoring bit. And I have 5 more minutes. So up to you. If you have any questions about anything specific, I'll be happy to answer. I also run anomaly detection in Agoda, alert correlation, so I can talk about that as well a little bit. Questions? Okay. Anomaly detection, 3 minutes, real quick. Interested? All right, so just real quick. I basically took the real-time monitoring bit to the next step, right? So, okay, we have alerts, we have events, we have all these different things going on at the same time. We have a very serious alert fatigue going on in Agoda. We are basically a data company that happens to deal with a travel website. But we have about 50,000 alerts per day, which is ridiculous. Like I'm not going to open my, so 50,000 emails or more coming in. So what I said, okay, listen, like I don't want to deal with alerts, and I don't want the company to deal with alerts. What I want is aggregated incidents, right? If I have a cluster of 200 servers that are roughly running out of memory, what I want is one alert saying 60%, you're partially functional, 60% of your cluster is running out of memory. That's it, done, right? Not 150 alerts, each one saying your server 2001, 2002, 2003, so on, is running out of things. So what you see here is I ended up building actually a service registry, which is a dependency graph of all these microservices in Agoda. And what I'm doing is I'm correlating things. So I'm coming up with hypotheses with, okay, what's wrong? Like if this service is dying, like why is this one dying? It may be related, the quarantine zone may be much wider, right? And I want NOC to call actually the root cause services, not go one by one, because right now that's what's happening. So NOC sees something dying, calls the team up, hey, your service is not running, right? And those guys log in, check. Half hour later, sorry, mine is fine. Like I'm just getting weird data. Maybe you could call the other service, and then so there's this ping pong thing going on. So that's where I suggested that I would correlate all these different events. So whether we're running experiments, whether promos are pushing more bookings in a specific vertical, whether maintenance brought down half of my servers or they just died. Deployment, sometimes different services that depend on each other, they deploy at the same time. We had this incident 2 weeks ago. Some guy, it was like 5 something, some guy just got kind of really itchy to go home, so he just put deploy parallel 200 servers, brought down the whole thing, so on. So I'll demo this to you guys real quick. So there's a dashboard with all the services, with all my DCs. These are the different alert types and the gravity of the alerts. That basically tells me, okay, this service is healthy, not healthy, and then off of this, basically, I can actually see what's going on with all the dependencies. The arrows are actually the dependency, the data flow itself, right? And you can see how the API content copy. I think. Actually, there are a couple of people from Agoda, so they might be familiar with these. You can actually see, okay, like what's going on? What are my alerts about? As I said, we have the Grafana alerting system. So here you have your alerts, tells you what's going on. The influencer events are the events that may not bring your service down, but may affect the way it works. So like experiments, promotions, maintenance, and so on. Okay, and then you can basically parse this, right, and then see. So as you can see, the CDB is a Microsoft SQL service, ES, Elasticsearch, DFCAS, Cassandra cluster, and then so on. Okay, last bit, anomaly detection, 2 minutes, and I'm done. So, same thing. We ended up building it in-house. There are actually quite a few really good solutions out there now, so I would recommend you look into it. The biggest challenge that I had with anomaly detection is that you think it's a technical challenge. It's not. It's actually much more of a people challenge. People don't really understand what anomaly detection is, and they just want to, they look at it as a bit of a silver bullet. So they just want to, hey, can you monitor my system with anomaly detection and let's just kind of automatically figure out what's wrong with it. So there's a lot of education that needs to be done, and you need to account for this. I do have data scientists on premise, so that makes it much easier. So I have a couple of algorithms that are Keras, PyTorch, so machine learning. I also went for the majority, because coverage is very important. So currently we cover about 4,000 time series and expect to grow very fast. So actually, you don't care for like super precise things. It's a very gray area. What is an alert and what is an anomaly and what is not. I'll show you in a couple of slides. So you want a simple algorithm, like a moving average or something like that, to a regression-based algorithm to just figure out where you're at with things. So this is what we focused on, starting simple, focus on business impact. So this is the 5th iteration of anomaly detection in Agora. The previous 4 failed miserably. People got fired and so on. So remember this, start simple, business impact is most important, right? In our case is booking loss. Make sure you focus either on precision or coverage. You cannot get both at the same time. I picked coverage. Make sure you can scale. And again, make it as self-serve as possible, unless you have hundreds of people helping you. So both on the onboarding bit and the investigation bit as well. Okay, so this is what my anomaly detection engine produces. So somebody reaches out to me and says, hey, can you check can you turn on anomaly detection for my system? Okay, I do my thing. And then in Slack, they get these alerts saying, hey, your this and that dropped. I see a drop or a spike. So basically what you end up doing in order to find outliers is you have to decompose your time series. So you have your level, you have your trend, then you have your seasonality or seasonalities, right? Your Friday might be, like your weekends might be very different from any day, right? And then you end up with noise, external regressors. These would be Christmas or Chinese New Year or stuff like that, uprising and so on. So besides noise and external regressors, then you end up with potential outliers, and that's what you need to focus on. So this is how decomposition looks like. So I decompose the left side into the 4 different things on the right side. What you're interested in is, these are the 4 categories of outliers. Spike, drop, trend change, right? You go this way, level shifts. And this is what I do in order to get to it. So I get the raw data, I clean the data, very important. So you'll always spend most of your time actually cleaning the data. You're smoothing it, you're cutting out the peaks, the drops, the whatnot. You have to prepare your data, no matter which way you go, regression or machine learning. And then you do the fitting and the estimation. So what you end up seeing here is the blue confidence interval, like the upper boundary, lower boundary. So as long as your time series is within, then that means you potentially don't have an outlier. So that's where you expect it to be. This is the actual algorithm that I'm using. It took months to, should we clip, should we not? 10%, this, that. And yeah, this is what you end up with. The detection phase, we ended up with 2 different types of detecting. And yeah, this is what you get. So this basically, I have the coordinator to understand what I need to do, when to run what, is all Scala. And then I have a farm of Python workers, so the actual detection and all that stuff in the model building is done in Python. We tried Scala initially, only Spark, this, that, but we ended up with this setup. So we might actually do the coordinators as well in Python. Everything is basically the models, right, and the caching, because you don't want to pull, the idea here is that your time series keeps shifting, so you don't want to re-pull the entire time series all the time. So you want to basically drop what you don't need anymore that's too old, and then just reattach what's new. Hence, you want to cache it as much as possible. So we tried to, there was a lot of fumbling with this, with my VP and the CTO. It's like, what is the KPI for anomaly detection? So the idea was to define precision, 50%. Precision basically means you have at least 50% are not false alerts. It's like you have more positive than false alerts. And then detect within a certain amount of time. Actually, the time itself doesn't really matter if it's 1 hour or 10 minutes or 5 minutes, but what you care for is what was the business impact of it, right? So in some cases, time series are more important or less important. All right, so these are some of the challenges that I wanted to mention. So in this case, like in some cases, what you get is your data points are basically so low, like the value itself is like 2, 3, 2, 3, 2, 3, and then the 3 goes to 4, right? Or the 3 goes to 2. Like percentage-wise, it's a huge thing, right? Like how do you decide if what is an outlier at this point? If you have 5,000 and then off of 5,000 it drops 10, or you add another 20, or like that's a bit more stable. But when you have 2, 3, 2, 3, 4, like it's very difficult to actually say, okay, like is this an anomaly or not? In some cases, it's just the data is just garbage. It's just pure noise, right? So I have to just let the service owner know, listen, I cannot work with this. I cannot. Intermittence is another problem. Data is not coming. It's actually quite a big problem, because now you need to take care for this. You need to mark this and then make sure that this doesn't end up in your fitting, in your model, because it's going to ruin your prediction going forward. So this was one of the senior managers reached out to me and said, why didn't you catch that drop there? So then I went, well, hold on. I started zooming out a little bit, smoothing up the data, and it turns out it's actually not a drop, but it's a trend change. So I should have caught the trend change, not whatever feels like it's a drop. So I have a lot of conversations like this with people. We're like, is this an anomaly? Is it not an anomaly? Which bit of this time series is an anomaly? So it's the whole anomaly detection thing is a very gray area. So if don't think an ideal, falls true kind of situation. And I said most of the challenges are actually coming from the teams. So when they start to see alerts from this as well, the initial excitement, hey, this is going to solve all my problems. And then they go, hold on, now I'm getting even more alerts, right? Or another person, can we set up a meeting to see what's going on here? Yeah, that's it. And then I presented this bit to you, the dependency graph thing. So that's it. Thank you very much. Sure.
I have a question about, in your opinion, why is the most crucial part, or the most difficulty to build up this solution? Yeah.
This whole thing?
Yeah, you're technically, yeah.
Technically, I think the vast amount of technology that's behind this. So I have Cassandra, I have Elasticsearch, I have Postgres, Timescale DB, I have Janus Graph, Tinkerpop, the GraphDB. So there's just such a vast. I had to change in Grafana writes code as well. Like we changed the code. It's just the vastness of all these technologies. Like you have to be very careful what you pick. So that's why I mentioned with Monix. Like the FS2, for instance, is probably just as good. But I picked Monix because it just made really sense of, okay, so my Kafka consumption and syncing is producing the same type of contracts as my asynchronicity solution that also uses Quill, that also does the same. So I think these bits are very important. Whenever you do something new, a new feature, just always give yourself a bit of time to look around. What's already there? What can you use? What integrates well with your solution? I think that's it. And for the most cases, perhaps a bit of a bold statement, but whatever problem you're trying to solve, most probably somebody else solved it already a few hundred times maybe. So definitely look around and then see if you can use things. Just more like gluing things together quite often than actually writing everything from scratch. Says me who wrote everything in-house. But yeah. So like today, if I would have to set up real-time monitoring, I would probably not write this thing from scratch, like real-time solution, right? There are definitely quite a few engines. If I'm already in AWS or like you have a lot of different tools to use there, right? But we run our own DCs, so that kind of gives me more freedom, but also more challenges. Yeah. Okay, sorry.
Yes,
Okay.
One question.
Sure, absolutely.
So you are running this at Agoda,
Yes.
right?
Yeah.
Which is part of the Booking group.
Yes.
Are they running this as well, or
Booking?
Yeah.
Not really.
So
They're actually quite behind.
what do they do?
They're actually. I'm not sure how much I am allowed to share. They're using a very different tech stack. They grew very fast. Booking. They're 10 times bigger than us when it comes to volume. And then they're having quite a bit of challenges with technology. So the different teams, like the data platform team that I'm part of, we're actually negotiating now with Kayak, with Priceline, with Booking, to just kind of come together. If you look at Expedia, they run the same backend. Everything is the same, just the front end is different, the different brands. And we're trying to kind of move towards the same approach as much as possible. But just collaborate from the different brands, just pick the best and then put it together. So they're, for instance, they are a Perl user with MySQL. So, okay, that's it. Just thank you. Just grab business cards. Again, if you're interested in anything, if anything just caught your attention, please shoot me an email. Let me know. I'm also hiring, so if you're interested in Bangkok, good food, many good things. Thank you.